I've got something here to eat, Prayag, so I'm going to turn my camera off, but I'm not leaving. I don't want people watching me eat.
Okay.
Yeah, I might do the same during the talk. Okay, I think it's probably time to begin. So welcome back to everyone. Our next speaker is Prayagdeep Parija from the University of Wisconsin at Milwaukee, and he will speak on random quotients of hyperbolic groups and property T. Go ahead.
Thanks everyone for coming. So I'm going to talk about random quotients of hyperbolic group and property T. So I'm going to start off with talking about random quotients of free groups, which you might have heard about as random groups. Then I'm going to talk about what's property T. And then I'm going to talk about how, to extend taking this business of taking random quotients from free groups to any hyperbolic group. And then I'm going to talk about some new results. So random quotients of free groups. So imagine you have a free group which is on two letters generated by A, B, A inverse, and B inverse. Think of BL as all the reduced words of length less than or equal to L in the above generators. So this is basically the word representation of the Cayley ball in the free group. And pick a number in 0 to 1 that will be your density. So a random set of relators is a BL to the D tuple chosen uniformly and independently from this set of reduced words. We'll say that a random quotient of F2 at density D at length L is a presentation F2 quotiented out by the normal closure of this random choice of relators. So F2 quotiented out by normal closure of R. And the space of all such presentation will denote by this G F2 L comma D. So that's an L. So that's the space of all presentations at length L and at density D. So once you have set this up, let's look at some theorems. So this is like traditionally has been thought of as random groups. So the big theorem here is the Gromov phase transition theorem, which says that for density less than a half, the share of presentations in this family of random quotients that are non-elementary hyperbolic, this limits out to 1. So you fix D constant and let L goes to infinity. Then the share of presentations that are non-elementary hyperbolic goes out to 1. So in other words, for D less than half, a random quotient, which I'm going to denote by Fn quotiented out by normal closure of R, is non-elementary hyperbolic. And if you pick a density more than half, you get that it's trivial.
Can I ask a quick question? What exactly D was on the previous slide? There was some notation which I didn't understand. What does
D
this...
is just a real number inside 0 to 1. So it can take like values between 0 to 1. So this GN F2LD is fix D constant, fix the group constant and let L change. That changes everything. That changes the space of all presentations.
So what does this notation mean? Like floor BL to the power D?
Oh, so BL is, so BL, okay, BL, I should write a cardinality on the left and right of it. BL, so BL, the number of reduced words of length L in the free group is about 3 to the power L, and can't be like is not usually a integer, so I have to write a floor in there. So think of this number as 3 to the power L, this BL. So that's the growth of the free group. Okay, so hopefully it will become clearer as we go on. So you take a bunch of relators, and as L increases, the number of relators increases. Then for D less than half, your random quotient is non-elementary hyperbolic. For D greater than half, the random quotient dies out and becomes trivial. So as L goes to infinity, the share of presentations being non-elementary hyperbolic goes out to 1. the share of presentations becoming trivial for density more than half also goes to 1. So, all right. So let's move on to the next character in our story, which is about property T. So the definition of property T is a group gamma has property T if and only if every affine isometric action of gamma on a real Hilbert space has a fixed point. So it's a mouthful, but so we don't need to really understand the meaning of this definition. Some examples of groups having property T are finite groups, which is because you'll be forced to have a fixed point, and a group not having property T is, let's say, Z. Think of Z acting on the real numbers by translations, then you will not have a fixed point. So Z is a group which doesn't have property T. Some other groups that don't have property T are the free group, and all cubulated groups do not have property T as well. So property T is an obstruction to cubulation. And this property T was invented by Kazan to study lattices in semi-simple V groups. So that's another class of examples of groups having property T. So in this context, we have an old question of Gromov. Does a random quotient of a hyperbolic group have property T? So the thing that is not explained here or like clear here is, what does random mean? So this question has been studied and it has some answers. In this density model of taking quotients and starting with free groups, the answer is yes. And this was studied by Zook and Kotowski, which says that for density more than 1/3, that means from all the available free reduced words of length L, let's imagine you take more than 1/3 of them, then your quotients start showing property T. So if you recall, for density less than half, so if you take less than a half or square root of the relators, your Gromov's theorem says that your quotients are non-elementary hyperbolic. So the Zook and Kotowski-Kotowski theorem combined with Gromov theorem gives you a phase, so density between 1/3 and a half, where your quotients have property T and they are non-elementary hyperbolic. So, we don't want trivial groups because trivial groups are they have property T just like that. So this is an interesting theorem because your quotients here are non-elementary hyperbolic as well as they have property T. So for a long time, people did not know too many examples of groups having property T, but this theorem just gives you lots and lots and lots of examples. All right. So, but what about random quotients of any hyperbolic group? So we saw that the random quotient of a free group has property T in the density model. But what about if you start with any hyperbolic group? So for that, we need to understand how to take random quotients of hyperbolic groups. So any hyperbolic group, how to take a random quotient of it. So this problem was studied by Ollivier. So where he says that if G0 is any non-elementary torsion-free hyperbolic group and XL, you consider any set of words of word length less than or equal to L. So it should be a large set of words that are exponentially growing with L. And you take and you pick a number D between 0 to 1. So that's missing from this slide. So a random XL to the D tuple chosen uniformly and independently from XL is this random set of relators. And so in the previous case of free groups, we had that this XL there was the reduced words of length L, and R was this BL to the D tuple, which was a number of slots in your tuple, choosing independently and uniformly independently from XL. So in the Gromov's theorem, we had that for density less than half, your quotients of the free group were non-elementary hyperbolic, and for density greater than half, your quotients were trivial. To study, and Ollivier studied the random quotients of any hyperbolic group. There, this theorem he came up with is quite and a lot more flexible. This tells us that you look at any set of words, reduced words, plain words, geodesic words, which represent your elements of your Cayley graph, and you pick uniformly and independently from it a density D set, which is this XL to the D tuple. Then for density less than half minus, so there exists a beta which depends on the kinds of word you have chosen and your group. What happens is that with overwhelming probability for density less than half minus beta, G naught over R is non-elementary hyperbolic. So the share of words or the share of presentations that are non-elementary hyperbolic limits out to 1 as this L goes to infinity. And the share of presentations that is trivial limits out to 1 for density greater than half minus beta. So this beta is 0 for the case of free groups and reduced words of length L. But for any group, this beta is going to be positive if you quotient out by reduced words, and it's going to be 0 if you quotient out by actually the elements of the Cayley ball. So
may I ask something about this 1 and 2? What's the difference between XL in 1 and XL in 2?
XL is the same thing. So this is a general theorem. You imagine XL is like any set of words, plain words or anything. So if you choose less relators, you get non-elementary hyperbolic quotients, less meaning in this density sense. And if you choose more relators, then your group is trivial.
I understand that. I just asking about node 1 and 2. What's the difference?
Oh, sorry. So the point here is that for beta equal to 0, and starting with any hyperbolic group G naught, if your words you choose from are the words representing the Cayley ball or the group element. So every group element has some word representative, like short-lex geodesic words. So if you choose from that, and that's like in a sense the correct kind of things to choose from, then you get the correct phase transition at half. So if you choose from basically elements of the Cayley ball, you will get the correct phase transition at half. For the free groups, the correct words choose from were reduced words. For any hyperbolic groups, the correct words to choose from are these short-lex geodesic words that represent the elements of the Cayley ball. Choose from the Cayley ball, you'll get your.
But it looks like what is on the right of XL is the same in 1 and in 2. Am I wrong?
They are the same in the case of free groups. They are different in a general, for a general hyperbolic group G naught. For the free group, words representing the elements of the Cayley ball are indeed reduced words. There is no difference. But for any hyperbolic group G naught, reduced words do not represent elements of the Cayley ball anymore. So, so for any hyperbolic group, if you choose from reduced words, then you're going to get a phase transition at a different time. Your words will become, or your presentations will become trivial earlier. So that's what this beta is representing. It's a phase shift.
Okay.
So imagine for G naught a surface group for density less than 1, like 0.45 or something, the quotients will become non-elementary hyperbolic, and density greater than 0.45, it will become trivial. It's no longer half if you use reduced words, or if you use if you quotient by the elements of the Cayley ball, it is indeed half for the surface group. Right. So the question of Gromov and Ollivier is that, can you find a set of words XL for which a random quotient of G0 has property T and is non-elementary hyperbolic? So basically the question boils down to, can you find a phase where your quotients have property T and they're non-trivial in some sense, because that will give you an interesting class of groups. So this was answered for free groups by Zook and Kotowski, and recent research has been going on. So recently, this was answered in a model of density, in a density model of random groups by Ashcroft. This paper came out a couple of months ago. And so we have another answer here, which is we have a model of randomness where for density less than 1/3 and half, the random quotients we get also have property T and are non-elementary hyperbolic. So this was, yeah, I was working independently using a different strategy and a different choice of XL. So the theorem we get here is, start with any non-elementary hyperbolic group with a symmetric generating set A, and we have a rather unnatural set of words to choose from, which is like DL minus 2 was your words representing the Cayley ball, but take those words and attach the generators at the beginning and end. So consider those set of words and choose XL to the D, choose XL to the D number of times from them uniformly and independently. So here we get that for density between 1/3 and half, these quotients do have property T and they are indeed hyperbolic. So there is no cost so in this model, there is no cost that we get by choosing from these sets. We get a full phase here of 1/3 to 1/2, where we have property T as well as non-elementary hyperbolic. So yeah, this DL minus 2, you can think of them as words representing the elements of the Cayley ball of length L minus 2, and then and that's where this unnaturalness comes from. You just have to attach generators at the beginning and at the end, consider the entire set, choose this many elements from them uniformly and independently, and as L goes off to infinity, the share of groups having property T as well as being non-elementary hyperbolic limits out to 1. All right. So I think that's all I have to talk about. Okay, thank you. Now let me go back to this slide so that if people have any questions.
Yeah. So in this theorem, is it for all D in this interval, or there exists one D in this interval?
Oh, it's for all D. For all D. Pick for any D. Yeah. Pick any D in between this 0.33 to 0.5. You will get this class of groups or class of presentations.
Okay.
And the share of presentations satisfying these properties limits out to 1 as L goes to infinity. So you fix D and then increase L. Yeah.
And what is with overwhelming probability?
So with overwhelming probability means so for example, in this Gromov situation, you fix your D, pick your favorite D, let's say for half, let's say 0.4, and look at this class of presentations that you got by quotienting from the free group. Share of presentations having a certain property, in this case, this non-elementary hyperbolic, that limits out to 1. That's what with overwhelming probability means.
So what is L here?
Oh, L is the length of your relators. So in this first case, L was the length of your, L was the length of the Cayley ball in the free group, and which was, we're really talking about words here. So it's the length of the Cayley ball, which can be thought of as reduced words of length L. As this Cayley ball increases and increases and increases, your family of presentations also increases because this tuple also increases.
So
yeah.
In this, can you go back just where you just this line with R? Does it mean that we take basically a D proportion of all?
Exactly. Yeah.
Okay.
Exactly.
That's
exactly.
A little bit cryptic notation because there is floor function and then raised to power D.
Yeah, I think I should have written like a brace on the left and right of it to like give the right. I forgot to put like cardinality on it, on the left and right of it, like this. So for the free group, for example, it's like the size of it grows like with growth 3, and this tuple will have like 3 to the power LD. And so there are 3 to the power L reduced words. You choose 3 to the power DL out of them.
Yes, understand. But it's always an integer. That's why you have this floor.
Yeah, exactly. Okay. Yeah.
And can we go to the slide where there is note 1 and 2 with beta? Yes. Could you explain informally what's the difference between 1 and 2? Beta I understand, but what is written on the right? Words representing elements in Cayley graph and reduced length of words length less than L. Looks like the same thing to me.
They are the same if the group you're starting with is the free group.
But in general also, because Cayley graph in some distance.
Oh, okay. Oh, sorry. I see. So I want to look at words that are in 1-1 correspondence with the Cayley ball. So for a Cayley ball in a general hyperbolic group, there are many reduced words representing the same element. So here words, when I say words representing the elements, I mean like unique words representing the elements.
Sort of normal form, yeah?
Exactly, yeah. So for any hyperbolic group, the correct kind of words to choose from are these your normal form words. If you quotient out from any yeah.
And in case 2, there will be XL will be larger because there are more words.
Yeah.
Okay, understand.
Yeah.
Okay.
Yeah.
Thanks.
For the free group case, they're the same. Yeah. I know that. Thank you very much for the
question session. Okay.
Yeah, thank you very much. It's boring otherwise.
Okay. Are there other questions for
Parag, can I ask a question?
Yeah.
For the Ollivier's theorem, what about D equal 1/2 minus beta? So this beta is already determined by x1 and g0, right?
Yeah, it depends on the kinds of words you choose from and the group you start with. So what happens at density equal to 1/2, I presume, will also depend on a lot of things. So I don't know what happens at exactly density equals 1/2. People have studied it for the free group, but not for any general group.
What about D equal 1/2 minus beta equal 1/2 minus beta? Because you only the Ollivier's theorem only consider about D strictly less than 1/2 minus beta and D greater.
Right. That's true. What happens at exactly equal? Yeah, that is unknown.
Oh, okay.
It depends on how you go off, how you're going off to infinity, sort of. People have studied for the free group, and there it depends on how it goes off. I mean, how these words are growing.
Okay, thank you.
Okay, are there any other questions? If not, let's thank the speaker. I'd like to thank him personally, but use any virtual way you can to express your appreciation.